Hello, this is Dr. Strickland. In this video, we will investigate the base-catalyzed halogenation of aldehydes and ketones and the halogenation of carboxylic acids. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So we've looked at the acid-catalyzed halogenation of ketones and aldehydes, and now we're going to take a look at the complementary reaction, which involves base. And one of the big differences is that in the base catalyzed version, the halogen is going to replace all of the alpha hydrogens. So you would look at your starting compound, like this one, for example, and go, okay, this is an sp2 hybridized carbon, so it can't be involved in this, but over here, this guy has two hydrogens attached to that alpha carbon. So the product is going to have both of them replaced, not just one of them replaced. And the reason for this is that the addition of a halogen atom to the alpha carbon increases the acidity of the remaining alpha hydrogens, so they're more easily removed than the first one. All right, so let's bring our general ketone or aldehyde back out. And I think we will go ahead and emphasize that hydrogen there on the alpha carbon. All right, and so in the base catalyzed tautomerization, the deprotonation comes first, and that's what we see here. So we're going to deprotonate at the alpha carbon, and these electrons up there, make that enolate ion that has a resonance contributor. An enolate ion is actually the conjugate base of the keto and enol forms. All right, so what I would like you to do is pause the video and draw me the resonance contributor for this enolate ion, and then come on back. All right, welcome back. So, I bet you did this. This is just the other resonance contributor for the enolate ion. And in this one, the negative charge is on the oxygen instead of on the carbon. All right, so the next thing that happens is that the electrophile adds. I'm just going to put that up here. And I'm going to do it with this right-hand resonance contributor, although you could use either one. Goes here. It's going to come over here and attack that guy. Kick out the halide ion, just like we've seen before. We need to leave that hydrogen up for what I'm going to show you next. All right, so I apologize for two squiggles. We reformed the carbon-oxygen double bond. And so now we've got a second deprotonation, because remember, all of the alpha hydrogens are going to be removed in turn. And if you had two alpha carbons that were sp3 hybridized and had alpha hydrogens on them, you would replace all of them. All right, so enolate ion number 2 looks like this. Same kind of a resonance contributor is formed. It's just that this one has a halogen and no hydrogens. All right, so we make this and this, and then a second electrophile adds, and it stops there only because we only have 2 alpha hydrogens. Otherwise, this could take place, multiple times until every one of them was replaced. So if you think about something like acetone, for example, acetone would have 2 alpha carbons. Both of those alpha carbons would have 3 hydrogens apiece. So you'd end up with a molecule that had 6 halogens in it. All right, so that's how that works. Now, in the base catalyzed halogenation, we don't ever see a protonation step, and that's okay. It's just a little different. Deprotonation, electrophile adds, deprotonation, electrophile adds. And so it would just be these 2 steps in sequence until you had used up all of the alpha hydrogens. So before we leave this, I want you to draw me the product of this reaction. So pause the video, draw me the product, and come on back. All right, welcome back. So the alpha carbon on the left is not in the running because it's sp2 hybridized. The alpha carbon on the right is eligible. And so these are bromines. So you have 2 bromines attached to that allylic carbon there. All right, so come on down here. Let's see how this is useful in making the compound that we talked about at the beginning of the chapter, and also this one. So if I do molecular bromine and acid, this is acid catalyzed halogenation. All right, where does the halogen go? All right, so pause the video, drawing the halogen. Come on back. All right, so your choices, of course, were that either we're going to replace one and only one, or replace all of them. And it depends on whether it's acidic conditions or basic conditions. Because it's acidic, it only replaces one. And so if you want to do this kind of a thing, where now this is like an alkyl halide, and we're going to do an elimination reaction, then I would want a big bulky base and heat. So, elimination reaction. If I wanted to do a substitution, if you use just a hydroxide ion, you're going to get a significant amount of elimination product along with this substitution product. So in general, people are more commonly mix this up with an acetate ion, which, as you know, just has the negative charge there on that oxygen. So this is a weakly basic nucleophile, strong enough to be SN2 because it's an anion, but because it's weakly basic, you don't get so much elimination reaction. And so what we formed here was this guy. So we've got an ester over here and a ketone over there. And then in order to hydrolyze this ester, we just need aqueous acid. Okay, so it's possible to take cyclohexanone, introduce an alpha halogen, and then go forward with a substitution process or an elimination process, which can be very handy when you're doing some synthesis problems. All right, so that's a story on alpha halogenation of ketones and aldehydes. If you want to use it with a carboxylic acid, things are a little fancier. And so if you follow the general reaction pattern here, let's see what changed. We've got phosphorus tribromide and molecular bromine in the first step, followed by water. And when all is said and done, what we've done is replace the alpha halogen. So the first thing I want you to do is use this pattern to predict this product and then come on back. All right, welcome back. So just the replacement of one of the alpha hydrogens with a bromine. And so we're not going to talk about the entire mechanism. You could do it because we've done the pieces of it before. In the first stage, the carboxylic acid, let's add pyridine up here. If you have PBr3 and pyridine, you can convert a carboxylic acid to the corresponding acyl bromide. Now, this acyl bromide will undergo tautomerization. And now we've got a bromine and a hydroxyl group connected to that same carbon. When this reacts with Br2, and we're still in step 1, then you get an electrophile adds right there. And now we've got bromines in a couple of different places. But remember that acyl halogens, acyl chlorides, acyl bromides are very reactive. And so right here would be step 2. Tell you what, we'll bring it back over here. You wouldn't need to add anything except some water to make it do this. All right, so just redrawing the same compound. Mix it with some water. The mechanism will take it back down to the carboxylic acid. And so, like I said, you could work through this mechanism if you like, but you've done this. You know, this is activation of the carboxylic acid. This is tautomerization. This is electrophilic addition. And then this is hydrolysis of an acyl halide. Okay, so let's just write that in. All right, activation of a carboxylic acid, tautomerization, electrophilic addition, hydrolysis of acyl halide. Acyl chlorides are more common, but acyl bromides exist also. All right, so that is the basic story on base catalyzed halogenation and the halogenation at the alpha position of carboxylic acids. If you have any questions, please send them to me.